Before this bridge existed, engineers faced a deep karst canyon with almost no easy path across it. The first challenge was not construction, but understanding distance, elevation, wind, and the terrain itself. Steel, high-strength cables, and laminated glass would eventually have to cross this enormous void. The span had to bridge steep cliffs, separated by hundreds of meters of open air. Survey teams measured elevation, alignment, and wind exposure before any permanent work could begin. Geotechnical engineers studied the fractured karst limestone to determine where the structure could safely transfer its loads. Only after comparing terrain and survey data could engineers lock the final crossing alignment. Core drilling revealed the condition of the rock below the future foundations and anchorages. A network of survey points now defined the future construction corridor across the canyon. With the alignment verified, the project was finally ready to move from investigation into heavy construction. Before foundations could begin, engineers first had to solve a basic problem: how to move people, machines, and materials into this remote terrain. Heavy equipment climbed narrow temporary roads where every load had to be carefully controlled. Crews stabilized exposed slopes and protected working edges before larger operations could safely begin. A compact staging area organized steel, tools, vehicles, and temporary equipment near the future bridge site. Temporary power, lighting, lifelines, and guardrails turned the remote mountain edge into a functioning construction site. The site was now accessible and operational, but the permanent foundations had not yet started. Engineers first confirmed the exact foundation position and the condition of the exposed rock beneath it. Powerful drilling equipment bored into the karst rock to create deep structural foundations. A reinforced steel cage was carefully lowered into each prepared foundation hole. Workers secured the reinforcement while survey teams checked centerline and elevation. Concrete was pumped into the reinforced foundation and compacted to eliminate internal voids. Layer by layer, the foundation took shape without any part of the future tower rising above it yet. Engineers verified dimensions, alignment, surface quality, and the starter connections for the future pylon. The foundation was complete. Only now could vertical pylon construction begin. The suspension cables would carry enormous tension, and that force had to be transferred safely into the mountain itself. Crews excavated anchorage chambers directly into the cliffside rock. Deep holes were drilled to receive the steel anchorage system. Heavy steel rods, plates, and reinforcement were positioned inside the rock chamber. Concrete was placed around the embedded steel, forming a massive anchorage locked into the mountain. Engineers checked the exact geometry, elevation, and position of the hidden cable connection points. The completed anchorage was now ready to receive the future main suspension cable. The anchor system was complete, but no cable yet crossed the canyon. The pylons would control the cable profile, so their center line, height, and top elevation had to be exact. Formwork enclosed the first reinforced section of the future pylon. Concrete was poured in controlled lifts to begin raising the support pylon. Segment by segment, the slender concrete pylon climbed above the canyon edge. At full height, The top support hardware was carefully lifted into position. Survey teams measured verticality, centerline, and top elevation before cable work could begin. Both support pylons now stood complete, with nothing yet connecting the open canyon between them. The towers were ready. The next challenge was creating the first physical connection across the void. Engineers prepared winches and pulleys to pull the first slender line across the canyon. A thin pilot line began its slow journey into open air. For the first time, a physical connection linked the two sides of the canyon. The pilot line then pulled additional temporary support ropes across the span. Workers began assembling a narrow temporary catwalk from both canyon edges. Safety nets, side ropes, and independent lifelines protected crews working hundreds of meters above the canyon floor. The temporary walkway extended step by step toward the center. Engineers checked how the completed catwalk moved under natural canyon wind. The temporary catwalk was complete, providing access for the next stage, building the main cables. Before pulling steel wire, engineers calculated the final cable alignment, tension, and sag between the pylons. Large reels fed high-strength steel wire into a controlled system of winches and pulleys. The first permanent wires were slowly pulled across the canyon. Each additional strand added more steel to the growing main cable bundle. The cable profile was carefully adjusted until its sag matched the required geometry. Workers compacted thousands of wires into a controlled, uniform cable shape. Wire by wire, the main suspension cable approached its final form. Engineers measured cable tension, alignment, and final geometry before approving the system. The main cables were complete, but no vertical suspenders or permanent deck existed yet. The future deck load would travel upward through vertical suspenders into the main cables, pylons, and anchorages. Each cable clamp position was measured precisely along the main cable. The first vertical suspender was attached to a permanent cable clamp above the open canyon. More clamps and suspenders gradually formed a repeating structural rhythm along the span. Engineers checked suspender length, verticality, and spacing before any deck module was lifted. The suspension system was ready. The permanent steel deck could finally begin to cross the canyon. The deck was divided into narrow, lightweight steel modules designed specifically for a pedestrian suspension bridge. Welders assembled the first shallow steel frame inside precision fabrication jigs. Multiple modules were fabricated in parallel to maintain consistent dimensions and connections. Every weld, dimension, bolt hole, and connection plate was checked before finishing. Protective surface treatment helped shield the steel against the humid mountain environment. The deck modules were complete and ready for transport, but none had yet entered the canyon. To control structural balance, deck modules had to be installed in a carefully planned sequence from both sides. The first lightweight module was moved to the canyon edge and prepared for lifting. Workers secured lifting slings, shackles, and guidelines before the module left its support. For the first time, a permanent deck module rose into open air above the canyon. Chain hoists and careful alignment brought the module into connection with the vertical suspenders. A matching module was then lifted from the opposite side to preserve balance. Module by module, two separate deck halves extended toward the center of the span. Engineers continuously measured balance, elevation, and symmetry as the deck advanced. Near midspan, each new lift demanded increasingly precise control of alignment and elevation. The two deck halves were now close, but one final gap still remained open. Symmetrical deck hoisting was complete. The last central opening would require a dedicated closure operation. Engineers measured the final central gap before fabricating and positioning the closure module. The final lightweight closure module was rigged for the most precise lift of the entire deck sequence. The module was slowly lowered into the remaining opening between the two deck halves. Chain hoists and compact hydraulic tools moved the steel by centimeters until both ends aligned. Workers began locking the final steel connections at midspan. Survey teams verified continuity, elevation, and the final geometry of the now continuous steel deck. The steel deck now crossed the full canyon, but the transparent glass floor had not yet been installed. Before glass installation, engineers finalized the lightweight metal handrail and pedestrian safety edge system. The first metal handrail sections were aligned and secured along the deck edge. Section by section, the safety edges extended along the bridge. Engineers checked handrail alignment, verticality, brackets, bolts, and edge safety. The metal safety edges were complete. The defining glass floor could now be installed. Each transparent floor panel used laminated glass supported within a carefully controlled steel frame system. The glass arrived in protective transport racks, separated and secured against movement or impact. Every panel was inspected for dimensions, edge condition, surface quality, and visible defects before installation. A vacuum lifting system was attached to the first panel for controlled handling. The first glass panel was lowered slowly toward its support frame and elastomeric pads. Panel by panel, the transparent floor began to spread along the bridge. Engineers checked panel seating, joint width, support pads, and edge clearances. The full transparent floor was complete, but the bridge still had to pass technical finishing and formal load testing. With the main structure complete, engineers began a full system technical review. Every glass joint, support pad, and edge clearance had to remain within controlled tolerances. Drainage, surface condition, steel details, and deck edge connections were inspected and cleaned. Compact sensors were installed to measure vibration, displacement, and structural response during testing. Technical finishing was complete. The bridge was ready for formal controlled load testing. Engineers divided the bridge into controlled loading zones and planned how every structural response would be measured. Compact test weights were positioned in carefully controlled groups along selected sections of the deck. Under load, instruments measured deflection, vibration, displacement, cable behavior, and the response of the entire structure. After loading, engineers rechecked the glass, steel deck, suspenders, clamps, cables, and critical connections. The bridge passed its final technical verification and was ready to move from construction into operation. After years of engineering and construction, the completed bridge finally stretched across the canyon. For the first time, pedestrians could cross the transparent floor above the enormous void below. What began as an empty gap between two cliffs had become a completed bridge suspended above Zhangjiajie's canyon.